Good evening, students. I hope all of you stayed at home and learning new things. Today, I discussing optical fibers. So the fourth chapter of applied physics. What are the optical fibers? Optical fibers is a thin tubes made up of glass or plastic in which the light is propagated on the basis of total internal reflection, so without any loss of light energy. These are the optical fibers. These optical fibers also called light pipes. So why it is called light pipes? As the water flow in water tubes, same as the light also transmitted or propagated in such type of tubes. That's why these are called optical fibers. So depending upon what principle the light is propagated from one end to another end, so through these optical fibers, yes, that is the total internal reflection. So what is the total internal reflection? So the total internal reflection is, so when light passes from denser medium to rarer medium, so denser means the medium whose refractive index is high, rarer medium is the refractive index of the medium is less compared to first one. When light passes from denser medium to rarer medium, if this is known as angle of incidence. When angle of incidence is less than the critical angle, what happens? The light passes from higher refractive index medium to lower refractive index medium. Suppose if you increase the angle of incidence, then that is equal to critical angle, then the light not passes into another medium, it passes through the interface of the two mediums, that is the line which separates denser medium and rarer medium. Along that line, this light is passes. In this case, the angle of refraction is 90 degrees. So the last diagram, if you observe, the angle of incidence is more than the critical angle, then the light ray reflects into the same medium, not transmitted into the another medium. This is known as total internal reflection. So due to this total internal reflection, the mirrors are formed, the diamonds are glittered, and water bubbles also glittered due to the sunlight, only depending upon this total internal reflection principle. What are the two conditions for the total internal reflection? The main important condition, the first condition is the light should passes from denser medium to rarer medium. Second condition is the angle of incidence is greater than the critical angle. Then only the total internal reflection takes place. So only when these two conditions are satisfied. So this is the construction of optical fiber. So at the center, so this small thin tube like our hair follicle, so this is known as core. Above core, this is known as cladding. Above cladding, there is a buffer jacket. Sometimes it is called buffer jacket. These are the three main regions or the parts of the optical fiber. One is core, cladding, buffer jacket. These are the three regions. So this is also known as the construction of optical fibers.
What are fiber optics? The term is used to refer to the technology where the energy of light is harnessed to transmit data, much like you would use an electric impulse in a copper wire. Since light travels at the speed of 300,000 kilometers per second, fiber optic technology has greatly reduced the time in which information can be sent and received via fiber optic cables. Optical fibers. An optical fiber is a semi-flexible, transparent and extremely thin strand of pure glass that has the diameter of a human hair. Thousands of these strands are arranged in bundles to make a thicker cable. A fiber optic cable is made up of 5 parts. Strands of glass that are bundled together to make one single channel for light to travel, called the core. The diameter of the core dictates how much information can travel at once. A protective sheath or coating of silica called cladding, which increases the total internal reflection of the core and hence prevents data loss. A layer of plastic surrounds the core and cladding to reinforce the fiber core. The strengthening fibers around the coating give added support to the coating. All this is covered in the cable jacket like any other cable or wire.
So, students, already you watched that video, some brief information about the structure of the optical fiber. So, the optical fiber mainly three regions. One is the core, second one is the cladding, third one is the jacket or buffer jacket or the sheath. So what is the core? The innermost region, small region. So in this diagram already we are seeing that region is known as core. So the innermost cylindrical region is called core, which is the light guiding region. This means that the light is only confined into the core. Generally, the refractive index of the core is more than the refractive index of the cladding. So the diameter of the core is 5 micrometers to 50 micrometers. So this is the area, cross-section area of the optical fiber. So core is innermost region. It is very small. Only in the core the light is transmitted or propagated. So above core there is in white region, that region is known as cladding. What is cladding? The core is surrounded by a middle region known as cladding. The refractive index of the cladding always less than the refractive index of core. Why? To satisfy the total internal reflection. So already we learned in total internal reflection, that is to take place that condition the light should passes from denser medium to rarer medium. That's why always the refractive index of the cladding is less than the refractive index of the core. Generally the diameter of cladding is 125 micrometers to 250 micrometers. The last region, so the last region, that the shaded region, is known as sheath or buffer jacket. So that is the outermost region, that's why it is called sheath or the buffer jacket. The sheath is the bodyguard to protect the cladding and the core from the abrasions, contaminations and harmful influence of the moisture. So generally these optical fibers are in the ground. That's why to protect this core and cladding, so sheath or buffer jacket is around the that core and cladding region to protect from all the conditions. It also increases the mechanical strength of the fiber. So these are the three main regions of the optical fibers. So optical fibers are constructed either as a single fiber or flexible bundle or a cable. So
I find this a fascinating object. It's a fiber optic cable for a stereo. I find this a fascinating object. It's a fiber optic cable for a stereo. If I shine this laser pointer down the cable, it guides the light out the other end. These cables are used to connect our world today and are capable of transmitting information across countries and oceans. But first, let me show you how it works. I have a bucket that I've modified with a window in front. And on the other side, I put a stopper in this hole right here. I have a bottle of propylene glycol with just a little bit of creamer in it. A ring stand. And of course, a laser pointer. Now, keep Keep your eye on this plug when I turn out the lights. That's wonderful. The light follows the liquid flow all the way to the bucket. Amazing. It does this because of total internal reflection. As the light enters the stream, it is reflected as soon as it hits the interface between air and liquid. You can see here the first reflection, and then the second, and the third. This occurs because there's a difference between the index of refraction of the guide material, here propylene glycol, and the outside, air in this case. Recall that any time light strikes a surface, it can either be absorbed by the material, reflected from it, or pass into and through it. The latter we call refraction. It's easier to see from a top view. Reflection and refraction can happen at the same time, but if a light ray hits the surface at an angle greater than the critical angle, it will be completely reflected and not refracted. For this propylene glycol and air system, as long as a beam hits the surface at an angle greater than 44.35 degrees, measured from the normal, it will propagate down the stream via total internal reflection. To create this same effect in an optical fiber, engineers create a core of glass, usually pure silicon dioxide, and an outside layer called cladding, which they also typically make from silicon dioxide, but with bits of boron or germanium to decrease its index of refraction. A 1% difference is enough to make a fiber work. To make such a long, thin piece of glass, engineers heat a large glass preform. Its center is the pure core glass and the outside the cladding. They then draw or pull a fiber by winding the melt onto a wheel at speeds up to 1,600 meters per second. Typically, these drawing towers are several stories tall. The height allows the fiber to cool before being wound onto a drum. One of the greatest engineering achievements was the first ocean-spanning fiber optic cable. Called TAT-8, it extended from Tuckerton, New Jersey, following the ocean floor over 3,500 miles until branching out to Whitmouth, England, and Ponmarsh, France. Engineers designed the cable carefully to survive on the ocean floor. At its center lies the core. Less than 1/10 of an inch in diameter, it contains 6 optical fibers wrapped around a central steel wire.